Today's video is an introduction to how to calculate equilibrium constants. In chemical equilibrium, we cannot assume that reactions are quantitative. This means that we cannot assume that at the end of the reaction, only products will be present. This also means that when there is not a limiting reagent in a reaction, stoichiometric calculations become a little more complicated. For this unit, you will need to draw something called an ICE table to organize your information. The letters I, C, and E stand for initial, change, and equilibrium, which correspond to the rows of the ICE table. Read through this sample problem and observe how the data is filled into the ICE table. Notice how the chemical amounts used in ICE tables are concentrations. Although it is not stated, we can assume that the initial concentration of hydrogen iodide is 0 millimoles per liter, because the initial container only had hydrogen and iodine gas. In the ICE table, we can see that we have information about the initial and equilibrium concentrations of the iodine gas. This means that we can calculate the change in concentration by subtracting the initial concentration from the equilibrium concentration. Because hydrogen and iodine have a 1-to-1 ratio, the same change would be expected for the hydrogen gas. To figure out the change for hydrogen iodide, multiply by 2 because the coefficient in front of hydrogen iodide is 2. This will give the final concentration for the hydrogen iodide. Systems that are in equilibrium follow the equilibrium law. The equilibrium law is an expression that is shown here. All of the uppercase letters correspond to chemical formulas, and the lowercase letters correspond to the coefficients. The closed brackets indicate that concentrations are used in the expression. The equilibrium expression is specific to each specific closed system at a specified temperature. Before you can write an equilibrium law expression, you must have a balanced equation. The product entities are written on the top and the reactant entities are written on the bottom in square brackets. The coefficients from the balanced equation become the exponents on the concentrations. If an equation is reversed, the expression would be a reciprocal of the expression above. If an equilibrium constant is high, there is a greater tendency of the system to favor the forward direction. Another important rule to consider when writing equilibrium expressions is that solids have a fixed concentration, and so they are not included in the expression at all. This means that we need to be aware of the states of matter for each entity. The equilibrium constant is typically written without units, because the mole per liter values will usually cancel out. Just remember that the constant has no units, but the concentrations are measured in moles per liter. Equilibrium expressions are usually written based on net ionic equations. This means that spectator ions are also omitted from the equilibrium law expression. This example gives a balanced equation and some information about the chemical amounts of each entity. Notice how the volume of the container and the number of moles are given. This will allow you to calculate the concentration of each entity. Begin by creating an ICE table. When drawing your ICE table, ensure that each chemical amount is written in moles per liter. Begin by writing in the values that are given in the question. You are given the amount of chlorine and carbon monoxide initially. You are given the amount of COCl2 initially, which is 0, and at equilibrium. Everything else will need to be solved for systematically. Since you know the initial and equilibrium concentration of the product, you can determine the change. Because the change is known, you can determine the change of the two reactants. Once you know the change for these, you will be able to determine the concentrations at equilibrium. Once the concentrations are known for each entity at equilibrium, the equilibrium constant can be calculated. There are several things that you need to remember about equilibrium constants. The equilibrium constant does not tell you how quickly a reaction occurs. It only tells you about the equilibrium expression. The equilibrium constant holds true for a wide range of concentrations. Temperature is the only factor that changes the equilibrium constant. Pure substances, solids and liquids, are not included in the equilibrium expression because they can't have a concentration. Gaseous and aqueous entities must be included in the equilibrium expression. The larger the value of the equilibrium constant, the more the products are favored. Now that you have finished this lesson, you should be able to write equilibrium expressions for any equilibrium reaction.